In a three-phase Delta-Wye transformer connection, the need for secondary conductor protection is addressed by the grounding of the Y-connected secondary. The primary side of the transformer is connected in a delta configuration, while the secondary side is connected in a Y configuration. The neutral point of this Y connection is typically grounded. This grounding plays a crucial role in protecting the secondary conductors from overcurrents. The grounded neutral provides a low impedance path for fault currents to flow back to the source. When a fault occurs on the secondary side, such as a short circuit or ground fault, the fault current will flow through the grounded neutral. This high current flow causes the overcurrent protection devices, such as circuit breakers or fuses, to trip or blow, interrupting the circuit and preventing damage to the conductors and equipment. Without a grounded neutral, fault currents would have a difficult time returning to the source, which could result in elevated voltage levels and increased risk of electrical shock or fire. The grounding of the neutral effectively limits the voltage and facilitates the operation of overcurrent protection devices. The overcurrent protection devices on the primary side of the transformer are designed to protect the transformer itself from overloads and short circuits. However, they may not always be fast enough or sensitive enough to protect the secondary conductors from overcurrents caused by faults on the secondary side. Therefore, the grounding of the secondary neutral provides an additional layer of protection specifically for the secondary conductors. It is important to note that the size and type of grounding conductor must be properly selected to handle the expected fault currents. The National Electrical Code, or NEC, specifies the requirements for grounding conductors based on the size of the transformer and the available fault current. Additionally, the overcurrent protection devices must be properly sized and coordinated to ensure that they trip or blow before the conductors are damaged. In summary, the grounding of the Y-connected secondary in a Delta-Wye transformer connection provides a critical path for fault currents, enabling overcurrent protection devices to quickly interrupt the circuit and protect the secondary conductors from overcurrents. This grounding is essential for electrical safety and the reliable operation of the electrical system. Let's delve into the specifics of how the grounded neutral aids in overcurrent protection. The effectiveness of the grounded neutral in protecting secondary conductors hinges on several factors. Firstly, the impedance of the grounding path. Secondly, the sensitivity of the overcurrent protection devices. And thirdly, the magnitude of the fault current. A low impedance grounding path ensures that fault currents can flow easily and rapidly back to the source. This is typically achieved by using a dedicated grounding conductor that is sized according to the NEC requirements. The grounding conductor should be connected to a grounding electrode system, such as a ground rod or a metallic water pipe that provides a reliable connection to the earth. Overcurrent protection devices, such as circuit breakers and fuses, must be sensitive enough to detect and respond to fault currents quickly. The trip curves of these devices should be coordinated to ensure that the device closest to the fault trips first, minimizing the extent of the outage. The magnitude of the fault current is determined by the voltage of the system and the impedance of the fault path. High voltage systems and lower impedance fault paths will result in higher fault currents. The overcurrent protection devices must be sized to interrupt the maximum fault current that is likely to occur. In a Delta-Wye transformer connection, the Y-connected secondary provides a convenient point for grounding the neutral. The neutral point is the center of the Y, and it is at the same potential as the earth. By grounding the neutral, a low impedance path is created for fault currents to flow back to the source. This path allows the overcurrent protection devices to quickly detect and interrupt the fault current, protecting the secondary conductors from damage. The NEC specifies the requirements for grounding the neutral of a Y-connected system in Article 250. This article covers topics such as the size of the grounding conductor, the type of grounding electrode system, and the location of the grounding connection. It is important to follow the NEC requirements to ensure that the grounding system is effective and safe. In addition to grounding the neutral, it is also important to provide overcurrent protection for each ungrounded conductor. This is typically done using circuit breakers or fuses. The overcurrent protection devices should be sized to protect the conductors from overloads and short circuits. The NEC specifies the requirements for overcurrent protection in Article 240. This article covers topics such as the size of the overcurrent protection devices, the type of overcurrent protection devices, and the location of the overcurrent protection devices. It is important to follow the NEC requirements to ensure that the overcurrent protection system is effective and safe. The combination of grounding the neutral and providing overcurrent protection for each ungrounded conductor provides a comprehensive system for protecting the secondary conductors from overcurrent. This system helps to prevent electrical fires, protect equipment from damage, and ensure the safety of personnel. To further illustrate the importance of grounding in a Delta-Wye transformer system, consider a scenario where the neutral is not grounded. In this case, a ground fault on one of the secondary conductors would not create a direct path for current to return to the source. This could result in a buildup of voltage on the ungrounded conductors, potentially exceeding the insulation rating of the equipment and creating a shock hazard. Without a grounded neutral to facilitate the flow of fault current, overcurrent protection devices may not operate as quickly or reliably, increasing the risk of damage to conductors and equipment. Furthermore, the absence of a grounded neutral can lead to instability in the system voltage, making it more susceptible to voltage fluctuations and transient overvoltages. These voltage disturbances can negatively impact sensitive electronic equipment and reduce the overall reliability of the electrical system. By grounding the neutral, the system voltage is stabilized, and the risk of voltage-related problems is reduced. In addition to protecting against ground faults, grounding the neutral also helps to mitigate the effects of lightning strikes and other transient overvoltage events. When lightning strikes a power line or nearby object, it can induce a surge of voltage on the electrical system. This surge can damage equipment and pose a safety hazard. However, a properly grounded system can help to dissipate the surge energy and protect the equipment and personnel from harm. The grounding system provides a low impedance path for the surge current to flow to the earth, reducing the voltage stress on the equipment. The effectiveness of the grounding system in mitigating lightning strikes depends on several factors, including the type of grounding electrode system, the size of the grounding conductor, and the proximity of the grounding system to the equipment being protected. The NEC provides guidance on the design and installation of grounding systems for lightning protection. When designing a grounding system for a Delta-Wye transformer, it is important to consider the specific requirements of the application. The size of the transformer, the available fault current, and the sensitivity of the equipment being protected should all be taken into account. A qualified electrical engineer should be consulted to ensure that the grounding system is properly designed and installed. In addition to the technical aspects of grounding, it is also important to consider the safety implications. A properly grounded system can help to prevent electrical shocks and other electrical hazards. However, a poorly grounded system can actually increase the risk of electrical shock. Therefore, it is essential to ensure that the grounding system is installed and maintained according to the NEC requirements. Regular inspections and testing of the grounding system should be performed to ensure that it is functioning properly. Any problems that are identified should be promptly corrected. Grounding is a critical aspect of electrical safety and the reliable operation of electrical systems. By understanding the principles of grounding and following the NEC requirements, it is possible to create a safe and effective grounding system for a Delta-Wye transformer. Furthermore, the coordination between the primary and secondary protection is vital for the overall system's resilience. Firstly, the primary protection, often fuses or circuit breakers, safeguard the transformer from overloads and faults originating on the primary side. Secondly, the secondary protection, including the grounded neutral and secondary circuit breakers, protects the secondary conductors and connected equipment from faults on the secondary side. The coordination of these protective devices involves selecting devices with appropriate current and time characteristics. The goal is to ensure that the secondary protection operates quickly to clear faults on the secondary side, while the primary protection operates only when faults occur within the transformer itself or on the primary side. This coordination prevents unnecessary tripping of the primary protection, which could disrupt power to a larger portion of the electrical system. Proper coordination minimizes downtime and enhances the overall reliability of the system. The selection of overcurrent protection devices for the secondary conductors should be based on the ampacity of the conductors, the characteristics of the connected loads, and the available fault current. The ampacity of the conductors is the maximum current that the conductors can safely carry without overheating. The overcurrent protection devices should be sized to protect the conductors from overloads, which are currents that exceed the ampacity of the conductors. The characteristics of the connected loads, such as the inrush current of motors or the harmonic content of electronic loads, should also be considered when selecting overcurrent protection devices. The available fault current is the maximum current that can flow during a fault condition. The overcurrent protection devices should be able to interrupt the available fault current without being damaged. The NEC provides detailed guidelines for selecting overcurrent protection devices based on these factors. Regular maintenance and testing of the overcurrent protection devices are essential to ensure that they operate properly when needed. Circuit breakers should be periodically tested to verify that they trip within the specified time current characteristics. Fuses should be inspected to ensure that they are not damaged or corroded. Any faulty or damaged overcurrent protection devices should be replaced immediately. In addition to the grounded, neutral, and overcurrent protection devices, other protective measures can be implemented to enhance the safety and reliability of the electrical system. Surge protective devices, or SPDs, can be installed to protect equipment from voltage surges caused by lightning strikes or other transient events. SPD divert the surge current to ground, preventing it from damaging sensitive electronic equipment. Harmonic filters can be used to reduce the harmonic content of the current, which can improve the efficiency and reliability of the electrical system. Harmonics are currents that are multiples of the fundamental frequency of the power system. They can cause overheating of equipment, distortion of the voltage waveform, and interference with communication systems. Ground fault circuit interrupters, or GFCIs, can be installed in areas where there is a high risk of electrical shock, such as bathrooms and kitchens. GFCIs detect small ground faults and quickly interrupt the circuit, preventing electrical shock. Electrical safety is a shared responsibility. Electrical workers should be properly trained and qualified to perform electrical work. They should follow safe work practices and use appropriate personal protective equipment. Building owners and managers should ensure that the electrical system is properly maintained and inspected regularly. They should also educate occupants about electrical safety hazards. By working together, we can create a safer electrical environment for everyone. Finally, let's consider the application of these principles in a practical scenario. Imagine a commercial building powered by a three-phase Delta-Wye transformer. The secondary side of the transformer is connected to a distribution panel that feeds various loads, such as lighting, HVAC systems, and office equipment. The neutral point of the Y-connected secondary is grounded to the building's grounding electrode system. Each circuit breaker in the distribution panel is sized to protect the conductors and equipment connected to that circuit. The circuit breakers are coordinated to ensure that the device closest to the fault trips first. Surge protective devices are installed at the service entrance and at critical equipment locations to protect against voltage surges. Ground fault circuit interrupters are installed in bathrooms and kitchens to protect against electrical shock. The electrical system is regularly inspected and maintained by qualified electrical workers. The building owner has implemented an electrical safety program that educates occupants about electrical safety hazards. In this scenario, the grounded neutral provides a critical path for fault currents, enabling the circuit breakers to quickly interrupt the circuit and protect the secondary conductors from overcurrents. The surge protective devices protect the equipment from voltage surges. The ground fault circuit interrupters protect people from electrical shock. The regular inspections and maintenance ensure that the electrical system is functioning properly. The electrical safety program educates occupants about electrical safety hazards. This comprehensive approach to electrical safety helps to prevent electrical fires, protect equipment from damage, and ensure the safety of personnel. The National Electrical Code serves as the cornerstone for safe electrical installations, providing detailed requirements for grounding, overcurrent protection, and other critical aspects of electrical system design. Adherence to the NEC is essential for ensuring the safety and reliability of electrical systems in all types of buildings and facilities. Regular updates to the NEC reflect advancements in technology and lessons learned from past electrical incidents, making it imperative for electrical professionals to stay informed about the latest code revisions. In conclusion, the grounding of the Y-connected secondary in a Delta-Wye transformer connection is a critical safety measure that protects secondary conductors from overcurrents. The grounded neutral provides a low impedance path for fault currents, enabling overcurrent protection devices to quickly interrupt the circuit and prevent damage. The combination of grounding, overcurrent protection, and other protective measures creates a comprehensive system for electrical safety and the reliable operation of electrical systems.